Okay, everyone, good morning. Last time we stated Coulomb's law. So let me write it down. Coulomb's law essentially has to do with two charges. So if I have a charge Q1 and a charge Q2, I can essentially mathematically write the vectorial force between them. Let's say I wanna find the charge that one applies, the force that one applies on two. So I write that as F1, 2. So this is the force that one applies to two. Right, so we said this is going to be some constant of proportionality, which we wrote as 4 pi epsilon naught. Epsilon naught is for free air or for vacuum. If it was anything else, it would be different. And then Q1, Q2. And then we will have to represent vectorially this direction, right? So this is going to be from 1 to 2, right? So it's going to be R2 minus R1. I could write this as, this is from 1 to 2. I could write this as R1, 2, right? And then I need to remove the magnitude of this vector from the equation. So I need a unit vector. So I divide by the magnitude of R2 minus R1. That's the first. So this gives me here the unit vector. But then also there's the inverse square law. So there is a dependency on the distance, on the inverse square of the distance. So I needed to add an extra square here. So this becomes to the power 3. So this is one way of stating Coulomb's law mathematically. And it all, depending on the sign of Q1 and Q2, the attractive property or the repulsive property just comes through instantly. If Q1 and Q2 are the same charge, everything remains positive. The direction of this arrow vector remains this in that direction. If the charges are of opposite direction, then the arrow reverses because I end up with a negative sign here. Okay, so the repulsive nature and the attractive nature occurs naturally. Let me see. I wanted to do last time an example. So let's do, see if I can get, let's do an example from the textbook. Let's do this example. Which I think we did, but let's redo it. That's fine. Paste. Okay. I have two charges located at 2 points in space. Clearly, they're located on the plane. Notice that the z-axis is 0. So those are located on the plane, really. So this is x, y. They're located at 1, 1. So this is Q1. This is P1.1. And then 3, 2, something like this. So this is 3. Let's see if I can do it. So this is 1, 1. So it's Q1, 1, 1, and then 1, 2, 3, 3, 2. So this is charge to Q2. This is P1, this is P2. So P1 is 1, 1, 0. P2 is 3, 2, 0. So I can represent the position vectors here. I can represent R1 and R2 easily here because it is a Cartesian system, right? The bases are constant everywhere. If it was, yeah, we said last time, it was anything other than the Cartesian system. Whenever you're dealing with position vectors, it's always best to stick with the Cartesian system. So R1 is going to be what? It's going to be 1x hat plus 1y hat. R2 is going to be 3x hat plus 2y hat. Calculate the force on Q1 and Q2. If Q1 is this and Q2 is this. Well, so we want to calculate both. So we want to calculate two forces. We want to calculate the force of one acting on two, which is Q1, Q2 over 4 pi epsilon naught. The distance between those, well, let me write it down. It's going to be, this is from 1 to 2, right? From 1 to 2 means I have to invert R1, right? So this is going to be R2 minus R1. You know, to get from the tail to the head, I need to invert R1. So R1 is going to end up with the minus sign divided by magnitude R2 minus R1 cubed. I'm going to use this form of Coulomb's law. And then I have Q1 is 2, 4. So it's going to be 8 times 10 to the power minus 18. 4 times 2 is 6. 6 times 10 to the power minus 18 over 4 pi epsilon naught, whatever that is. And then R2 minus R1 is going to be 3x hat minus x hat is going to be 2x hat. 2y hat minus y hat plus y hat. So this is R2 minus R1. R2 minus R1 magnitude is what? Is going to be 2 squared, 4, plus 1 squared, 1, which is going to be 5, square root. This is the magnitude, and then to the power 3, 3 over 2. So it's going to be 5 to the power 3 over 2. And then we can calculate whatever that is. If 2 acting on 1 is going to be exactly the same, but with R1 and R2 inverted. So everything is going to be the same, but R1 and R2 is going to be inverted. So I'm going to have here R1 minus R2. R1 minus R2 is going to be, it's all going to be the same. 6 times 10 to the power minus 18 over 4 pi epsilon naught times 5. Of course, you know what epsilon naught is, 8.854 something, right? But then we're going to have here R1 minus R2. R1 minus R2 is going to be x minus 3x. It's going to be minus 2x hat. And then y hat minus 2y hat is going to be minus y hat. So there's going to be a negative sign. Notice it's going to be, is it the same vector? Yeah, take the minus out. It should be the same vector, should be the same direction, but opposite. So if I take the minus out, we're going to have a minus sign here, right? And it's going to be 2x plus y. So yeah, it makes sense. Everything makes sense. Notice it's the same vector here, same vector, but one is saddled with a negative sign. So one of the forces is opposite to the other. So the forces will always be, in a way, the Newton's third law still applies, although we're talking about electrostatics here, not mechanics. Turns out Newton's third law is more fundamental than just mechanics. Even in Coulomb's forces, any force really, doesn't matter what interaction or what force, one acting on 2 is going to be opposite of 2 acting on 1, opposite and equal. So this, so that's part 1 of the question. And I guess the idea here is to put a negative charge to show you that the force becomes attractive, essentially. That's the idea of the second one. So let's do another example. Did he get the same result as me? Let's see. 2 acting on 1. What did I get? 2 acting on 1 is negative. Yeah, 2x plus y. And 1 acting on 2, did he do that? Well, it's the same result. It's 2 over square root 5 cubed. So no, there's an extra 5. So it's 5 to the power 3 over 2. This is 5.5, and this is 5 2 over 2. So it becomes 5 to the power 3 over 2. So it is the same result. Okay. Of course, this is all in Newton. Let's look at this example now. This looks like an interesting example. Oh, this has a bit of mechanics in it. So we have to know what the centrifugal force is, mv squared over r. But let's look at this problem. Control-Shift-S. So this is a simple model of a helium atom and the electrostatic forces involved. Okay. Again, no dynamics. So consider the following model of the helium atom. The atom has 2 electrons and 2 protons, which we know about the helium atom. Assume that the electrons are stationary, which they are not, of course, as shown in figure, well, a snapshot in time at least. And the 2 protons are located at the center, at a point. Given the electric mass, ME, electron mass, 9.107 times 10 to the minus 31 kilogram, it's really tiny. The distance here is 0.5 times 10 to the power minus 10 meter. And the charge of the electron, we call it E, is minus 1.6 negative times 10 to the power minus 19 coulomb. Calculate the force between the 2 electrons and the force between oh, the assumption is that the electrons are opposite each other like that. Okay, so yeah, the force as a magnitude, let's calculate it as a magnitude, is going to be E squared, right? It's going to be a repulsive force, 4 pi epsilon naught. The distance squared, which is the distance is 0.5 times 0.5, 10 to the minus 10. It's going to be 1 times 10 to the minus 10 squared, right? That's it. K is 1 over 4. This is the magnitude of the force. This is the direction of the force, right? So this is going to be 1.6 squared times 10 to the power minus 38, I think, minus 20 is minus 40, plus 1. It's going to be minus 38 over 4 pi epsilon naught, 1 times 10 to the power minus 20. Okay, so this ends up being 1.6 squared over 4 pi epsilon naught. 10 to the power 20 goes up there. It's going to be the minus 38 plus 20, 18 times 10 to the power minus 18 Newton. The unit is Newton. Right, so this is the force between the 2 electrons and the force between each electron and proton. The force between, so this is EE, and then the force between EP is just going to be minus 1.6 times, the proton has the same charge as the electron, so it's going to be minus 1.6 squares times 10 to the power minus 38. Okay, it's going to be the same, but the distance is now 0.5 times 10 to the power minus 10 squared. So it's going to be minus 1.6 squared over 4 pi epsilon naught. 0.5 squared is a quarter. So quarter of 4, the 4 goes away. And then 10 to the power minus 20, I end up with 10 to the power minus 18. And then what's the second part? Neglecting all the forces within the atom, what must the angular velocity of the electron be to stay at a given distance from the nucleus, assuming that the two electrons are always at the same relative position? Okay, so this is an idea that the idea here is that there are repulsive forces. So the two electrons repulse each other, and then there is an attractive force, right? So the idea is that there's a difference between the two forces. So we calculated this. So we calculated on a single electron here, we calculated the repulsive force, how much the other electron is trying to push the electron away. And then we calculated how much a single proton is attracting, right? I think here we have to multiply by 2 because there are 2 protons, actually. So there is multiplication by 2. But anyway, I mean, the whole point of this problem is you have a repulsive force and an attractive force. The question is, you want a stable orbit, right? So to get a stable orbit, the forces have to be equal. Because the electron is rotating, there's also something called the centrifugal force. There's something, whenever you rotate, there's something that tries to push the electron away. This is just a problem of making sure that all 3 forces are equal. Once the repulsive forces and the attractive forces are equal, we get stable orbit. I think that's the point of the problem. So here he calculates FEE, positive forces between the electrons. He calculates the attractive force between one electron and the 2 protons. That's why there is a multiplication by 2 here, right? And notice the forces are not equal. This is not a stable. There is some extra force that needs to be there, and that extra force is the centrifugal force. So he calculates the difference. He sums up the forces. And the difference between them, one is positive, one is negative, has to be the centrifugal force, which has this equation, and that tells you what the velocity of the electron needs to be. So he solved what you're solving for is that in this unstable situation, where the repulsive force is higher than the attractive force, what should the extra centrifugal force be to keep the electron from flying away? And that's what he calculated here. So, okay. The electrical field. So this is the electrical force, electrostatic force. We need now to introduce the concept of the field. The idea here is that I have two charges, Q1 and Q2. And the model as it stands right now is the model of an action at a distance. It's similar to 2 planets or 2 masses and gravity. So the idea is that the two charges act with each other at a distance. So this is not a dynamical model. This is not a true model. And it invalidates something called locality, meaning that nothing can instantly travel at a distance. So the idea came to a guy called Faraday that what if there's something emanating out of one of the charges called the electric field, and that thing emanating reaches close to Q2 and affects Q2. So the idea is that there is something around in space, around where Q2 is situating, that is acting on Q2. And that is what's causing the force. And that thing that's in space, situated in space around Q2, is the electrical field. How do we quantize or measure the electric field? The problem here is that we can measure it using the force, but the problem here is that having a charge here at that point in space distorts the field. So what we want to do to figure out, calculate what the field is, what is this thing that's emanating from Q1 and reaching this point, gets distorted by Q2 itself. So how do we can find out what's reaching this point without the effect of Q2? We can make Q2 as small as possible. Right, so the idea is to make Q2 approach zero. If we make Q2 approach zero, the limit of the force that Q2 feels at that point, as that charge approaches zero, is essentially the field at that point. It's a way of measuring the field at that point. So if I have Q, charge Q, and I'm imagining something emanating from it, and it reaches a certain point P, and I want to find a way of calculating that field there. So what I can do is I can bring in a test charge. I can bring in a QT test charge and put it there. If I bring in a test charge, what would the force be here? The force emanating from Q at that point P is going to be QT test charge over 4 pi epsilon naught let me write this as R. I need to write the vector from Q to P. What's that? That's going to be RP minus RQ, position vectors, right, over RP minus RQ cubed. Now the idea is that I want to take my test charge to be zero. So I want to take FQ divided by QT and take the limit as QT approaches zero. Does this limit exist? Yes, because when I divide QT here, it goes away, right? So this becomes Q over 4 pi epsilon naught RP minus RQ. So this is the position of the charge. So that is the source of the field. This is the position of the point where I'm interested in calculating the field over RP minus RQ cubed. Right? This limit exists clearly, right? QT is not part of this equation. This is what's called now the electrical field due to Q, due to the charge Q at point P. I can write it like this. Or I can write it like this. It's just the electrostatic force at that point taken to the limit as the test charge goes to zero. And there is a specific limit here that equals this thing. Notice the test charge is not part of the equation anymore. All we have is the value of the source charge. Okay, so this quantity is called the electrical field, and its units are Newton per Coulomb. So now we don't have to worry about two sets of charges. Now we have like a single charge. We can write its electrostatic field. What if we want to find the force from the field? Like the force, because the fields exist, but it exerts force on anything. It's like a wind field. Like you put a mass and the wind field, or an ocean current field, right? Ocean current field, it's there, but you put a mass and it starts moving the mass. You put different masses, it moves the masses differently, right? The force depends on how much mass you have. So in the same way here, we have a charge, we know the field it produces at every point in space. How can we tell what force the field exerts? right? So now it's a change in perspective. When we put a charge here, let's say Q2, we don't talk about this charge Q acting on Q2. No, we talk about Q generating a field, and then this field locally acting on Q2. So it removes the action at a distance concept and introduces us back into a more intuitive local action concept, right? It kind of like, it makes more physical sense. It's kind of like if something happens far away, the old picture was if something happens far away, it instantly affects us here, which is a very non-physical picture. While the physical picture is that something happens far away, it propagates through space, reaches us here, and then whatever reached us here is affecting us here. So it brings in a local picture. Right. So we can get back the electrostatic force from the field by just multiplying Q2 times the field. Right. So the force is just the charge times the electrical field. Q2 times, let's say we have a second charge, and then the electrical field for a point charge, and we achieved this from Coulomb's law. So the electrical field at every point in space from a point charge, so I have a point charge, Q, the electrical field at any point in space, P, this is a random point in space, P, is just going to be Q over 4 pi epsilon naught, and then RP, this is the origin, this is the vector from R to the source, and this is the vector, position vector from R to the point in space, right? Over RP minus RQ, magnitude cubed. Right, this is the expression for the electrical field for a point charge, which we obtained easily from the Coulomb law. And then if you want to find the force at P on a charge Q2, then that force is just going to be Q2E at P. Take the field, multiply it by the charge at the point in space, you get the force. The field has Newton per Coulomb, and of course the force is just Newton. Okay, so this is the concept of the electrical field, and with the help of Coulomb's law, we know how to write the electrical field for a point charge. And now, from now on, it's going to be easier to always calculate first the electrical field and then worry about the force. So we won't worry about the force firsthand. The problem shifts to the problem of finding what the electrical field is. And then after we find the electrical field, we can determine what the force is on any charge in space. The question is, how do we calculate the electrical field in general? Right, so here we can deal with the electric field for a point charge, right? The basic concept here is something called superposition or linearity, right? The idea is that I have a point charge. I can calculate E emanating from the point charge. What if I have a number of point charges, not just one? So the idea of superposition, and superposition comes from the fact that electromagnetic theory is linear, right? Meaning that if I have multiple sources for the field, then I want to write the field at P, point P. The field I can consider only this to exist and find the field due to this. I then consider only this to exist, find the field due to this. And then the total field at P is going to be, the field at P is going to be just the sum of all the individual contributions. This is because electromagnetism is linear. Superposition applies. And this is like it does not, superposition in general does not apply for any random theory. The theory has to be inherently linear, and electromagnetics is linear. So let's say I have here Q1, Q2, Q3, Q4, Q5, Q6. What is the electrical field at point P? The electrical field at point P is going to be the sum of all those individual charges. So it's going to be Q1 over 4 pi epsilon naught. Let's call it RP minus R1. R1 is the position vector of Q1. This is O. This is going to be R1. This is going to be R2, so on and so forth, over RP minus R2 cubed, and then plus, now the second contribution from Q2 is going to be Q2 over 4 pi epsilon naught dot dot dot. So I can write EP at point P as the sum from K equals 1 to 6 of QK over 4 pi epsilon naught RP minus RK over RP minus RK magnitude cubed. So summing, and this is, by the way, a vector addition. Each one of those terms gives me a vector. And then I sum those 6 vectors up, I get the resultant field. Okay, then it doesn't matter. I wrote in 6 charges. What if I have 1,000,000 charges? 1,000,000. That's fine, I have 1,000,000 terms here. What if I don't have point charges? What if I have a distribution? What if I have, let's say, a charge that's on a wire, and I have a line charge density, rho L, Coulomb per meter? That's fine. I can divide this into an infinite amount of small segments, and then superposition still applies. Each small segment is going to have a charge of rho L dL, right? Typically, when we represent something happening at a source element, a differential element happening or existing on a source of the electrical field, we use prime, dl prime, just to indicate that this is a source of the field, not space. We have to differentiate between integrating over space and integrating over the source. So the source here is in this line. So this is going to be the charge of each segment. And we just sum over all the segments. What is the summation over what is an infinite summation? What is the summation of an infinite amount of segments? Infinitesimal segments. It's an integration, right? So E at P, this is point P. So this sum here, because it has an infinite number of elements, turns into an integral. So E at P is going to be the integral. Let's call this, right? Let's call this the origin. And then I have the position vector of the segment here. So this is R, I don't know what to call it. I want to call it in a way that kind of like should have a parameter that represents that varies. So this could be R prime to indicate that this is a position vector on the source, and it's going to be L, R prime L. Okay, L prime, sorry. Parameter L prime. Okay, so when L changes, when we are at a different point, R changes. Okay, so this is a sum going to be summing over dl prime. So this is going to be the charge at every segment is going to be rho L dl prime. Again, I'm applying the electric field law of a point charge as we obtained it from Coulomb's law. So you have the charge over 4 pi epsilon naught, and then the distance from here to the point is going to be Rp right. This is Rp. Is a constant vector minus R prime L prime over Rp minus R prime L prime. The notation might differ in the textbook. I'll check on it later. Cubed, and it becomes an integral. I mean, if you see this integral, don't get scared. All it is, it's the same summation here. But now, because we have an infinite number of charges, the summation turns into an integral. And same thing is going to be for surface charges and volume charges. We can always divide those distributions of charges into an infinite amount of segments. And each segment, we can consider it to be a point charge. And then we can calculate the electric field of each segment, small segment, and then get the total field through integration, either single line integration, double integration, or triple integration. So this is the beauty of linearity and superposition. Once we know the electric field from a point, we know the electric field of any charge distribution. We're done. All that's left is a matter of calculation. And we're going to do some calculation, a bit of calculation. Okay. Something I wanted to bring up, there's the concept of electric field lines. When you hear electric field lines, what are electric field lines? When someone draws electric field lines are different from the electric field. Like when you see sometimes those diagrams of like electron, proton, and then field lines like this. So this is a good way of representing the electric field. Of course, sorry, this is the electron, because this is the electron. The field lines are going to go from positive to negative. So they're going to go into the electron and out of the proton. What do those lines mean? Called lines of force. Those are not the electrical field. Those are the tangents of the electrical field. So the idea of those lines is that at every point in space, let's say this point, the electric field is going to be a tangent to this line. So this is going to be the electrical field here. This is going to be the electrical field here. So the idea is that you go at every point in space, and at every point in space, the electrical field is going to actually be tangent to those lines. So those lines that people draw are really the tangents of the electrical field. Right? At every point in space, it kind of like encodes the direction of the electrical field. Those are, it does not encode the strength of the electrical field. Well, it does indirectly by how crowded the lines are. If you have more lines close together, it indicates higher flux, higher electrical field. Right? That's the way it encodes it, but it does not encode it directly. It only encodes the directionality of the field. So let's say here, the field is moving in this way, and this is its tangent. Right? So it tells you the direction of the field at every point. That's what electrical field lines encode. Let's see. So there are number of, I mean, we can solve a number of problems. I wanted to get into a particularly really useful problem. It's going to show up later, which is the electrical dipole. I guess before I get into the dipole, let's do maybe another example first. See if there's an example I want to do. Oh, by the way, one way to just to I might have written the terminology a little bit different here, but let's stick to the terminology of the book. The terminology of the book is that if you have n number of charges, I equals 1 to n, then the total field is going to be qi over 4 pi epsilon naught, and then rp minus ri. Ri represents the position. I think this is what I did. Oh yeah, this is what I did. I just used k instead of I. So okay, so I didn't do anything different. And then over rp minus ri magnitude cubed. Another way of writing it is I equals 1 to n qi over 4 pi epsilon naught. We can use this notation, r hat, and we're going from I to p. So ip, remember? We use this condensed notation, right? So this means the position vector, unit position vector from I charge to point P over RIP magnitude squared. The cubed went away because now I have a unit vector here. This is equivalent to this. All right. So there are a bit of examples, and we can do a bunch of examples in the homework where we have multiple charges. But I wanna work out in the class a really important special case, which is what's called electrical dipole. What is the field? And this might seem like silly. Why should we care? It turns out the electrical dipole is important. The electrical dipole simply is the problem of finding the field due to two equal charges that are equal and opposite. So you have, let's say, two charges, equal and opposite, with a distance d between them. That's why it's called a dipole instead of a monopole. A charge point charge by itself is called a monopole. The idea is that we are interested in what the field is really far away. What would the electric field for this dipole look really far away, where the distance d and the orientation of the dipole does not really matter that much. I mean the orientation matters, but really the distance. So let's take the center of this distance, and let's take some position vector r really far away from the dipole to a point in space. R is going to be, let's call it RP, or I don't know, let's call it RP, the position vector of the point in space, minus RD, the position vector of the dipole. Okay, so the idea is that what happens if R magnitude is much larger than D? If R magnitude is much larger than D, it doesn't matter where the origin of the position vector is. I could put it in the center, that's fine, right? What would the field look like for that dipole? And the key thing here is that we can approximate. So let's do the derivation. So let me draw the dipole. Q plus, Q minus. I'm exaggerating here the distance between the two charges. Right? And then I have the center point here. I can write a vector from Q minus, and I call this R2 equals D over 2. So D is the vector that goes from Q minus to Q plus, right? And then R1 equals D over 2, okay? And then I have the point P far away. And then I have this distance here. This is what, and then I have this R here. I have this angle theta. What does angle theta represent? The angle, right? The angle with respect to the axis of the dipole. So if angle is 90, that means we have the dipole and we're 90 degrees from the axis of the dipole. If the angle is 0, that means we are in the direction of the dipole. So it's just a way of measuring the directionality of this point with respect to the orientation of the dipole, essentially, with respect to the point in space. That's what this angle measured. And this is R. This is the distance from the center of the dipole to the point P. Using that, we can reconstruct those two vectors, right? So here I have this vector is just minus R1 plus R, right, from vector calculus. So this is going to be R minus R1. You see that, right? So if I take minus R1 plus R, minus R1 plus R gives me this vector, right? So minus R1 plus R is just R minus R1. And this is going to be minus R2 minus R2 oh, no. So R is going to be R1 plus whatever vector is I'm going to try to write. So whatever vector is here is going to be R minus R1. Okay. R now in terms of the I'm trying to figure out what this vector is, right? So this is going to be, let me see. So this vector is going to be minus R1 plus R. What about this vector? Oh, yeah. This vector is clearly R2 plus R. So this is R2 plus R. You see that, right? To get this vector, I need to traverse this way. When I traverse this way, I go minus R1 plus R. To get this vector, I need to traverse this way. Sorry, I need to traverse, I'm confused a little bit. To get this vector, I need to traverse this way. Traversing this way is R2 plus R. Okay, so this upper vector is R minus R1. This lower vector is R2 plus R. Why do I want those two positional vectors? Because I want to write the electrical field due to, at point P, due to the negative charge, which is going to be minus Q over 4 pi epsilon naught R plus R2 over R plus R2 magnitude cubed, and then E due to the positive charge, it's going to be Q over 4 pi epsilon naught R minus R1 over R minus R1 cubed. And now the total charge is just of the dipole. A total electrical field of the dipole is just the superposition of both of them. We just sum them up. So Q over 4 pi epsilon naught is a common term. So I end up with Q over 4 pi epsilon naught. And I end up with R minus R1 minus R plus R2, right, over magnitude R minus R1 cubed, R plus R2 magnitude cubed. And then I'm going to substitute, instead of R1, D over 2. R2 is also D over 2. It's the dipole vector, and then the vector that goes from the negative charge to the positive charge, d over 2, instead of R2, d over 2. Everything becomes d over 2. Okay, so this term is interesting. See, do we have? Okay, I'm gonna continue this derivation next time.